and my name is Liam. We are both Canadian engineering students from the University of Toronto.
We have been taking part in the Tall Timber Research Initiative here at the University of Queensland, seeking to move towards a fundamental design philosophy for tall timber structures. The question we have been addressing is, how should tall timber buildings be designed?
To approach this question, it is first important to understand the material we are working with. Too often, mass timber is used inefficiently by directly substituting it in place of concrete and steel in existing structural systems. We, however, would like to first examine the material properties of wood so we can use them advantageously in the development of a timber structural system.
This short clip will outline the three major design considerations in tall timber buildings. Firstly, structural, then foundations, and lastly, fire safety. Our goal is to advantageously utilize wood's inherent material properties to guide the design of a tall timber building.
What becomes immediately obvious is that dealing with wood, we have a much lighter material that is weaker in flexure, combustible in nature, but has an incredibly high strength-to-weight ratio. The inability of some, including the codes, to look past the combustibility of wood has led to a lack of structural innovation with this renewable construction material.
Structurally speaking, there are two main factors to design for: gravity loads and lateral loads. Since wood is a less dense material, there's significantly less demand on the structure from self-weight. In terms of restraining lateral loads, a well-known principle in building design to increase bending resistance is to shift material out from the geometric center of the building.
With wood, we can no longer create geometries that rely on high flexural strength, as we could with concrete or steel, but must utilize wood in such a way that the building's geometry will compensate for its lack of flexural strength. A common feasibility study referenced in tall timber building design is the Tall Timber Project by Skidmore, Owings, and Merrill. They begin with a wooden core and shift the material towards the perimeter with the addition of timber shear walls to achieve the desired bending resistance.
Instead of starting with a traditional building core, we propose to begin by placing wood at the exterior of the structure, functioning as the building's lateral restraint system. This effectively increases the bending resistance through an increase in second moment of area. In less demanding designs, this material can be shifted in and function more as a core. We are not proposing a structural system such as the existing tubular form, but instead are proposing a design approach that utilizes geometry to compensate for wood's reduced flexural capacity.
Key considerations in the design of a foundation are bearing capacity, uplift forces, and overturning moment. As a less dense material, there are reduced gravity loads, and thus reduced bearing pressures exerted at the bottom of deep foundations. This could lead to smaller, lighter foundations for timber buildings. However, as we increase the height of tall buildings, overturning moments increase non-linearly with height, and thus foundations must be carefully designed to resist the resulting uplift forces.
The advantage also of shifting material out and the associated increase in second moment of area is the fact that there are reduced axial stresses from lateral loads. This helps to mitigate uplift. The real considerations in designing foundations for wooden buildings is balancing the benefits and consequences of reducing building weight due to the decreased density of wood. This is in part aided by the philosophy of keeping wood at the exterior of the building. In terms of fire safety, key considerations are self-extinguishment and delamination.
The chemical composition of wood causes it to be combustible. However, the thermal properties are such that after ignition, in the absence of an external heat source, wood fails to sustain a flame. Understanding this self-extinguishing property of wood is critical to designing fire-safe timber structures. The question designers should first be asking themselves is fundamentally, under what circumstances will timber self-extinguish? In addition, designers need to consider the possibility of delamination. This property must be well documented and researched, as it is critical to self-extinguishment because delamination increases the fire load. This increase in fire load will likely delay the point of self-extinguishment.
Both the standard fire test and the standard combustibility test deny wood the possibility of undergoing self-extinguishment. The re-radiation of heat from the furnace or coil back into the wood is problematic, as this process acts to sustain a flame on the mass timber element. A typical building fire, unlike the standard fire curve, will eventually decay, allowing for self-extinguishment to occur. If one can ensure that structural integrity is maintained up to the point when the fire load is consumed, wood will then undergo self-extinguishment. Understanding these two key properties of mass timber is crucial to move away from relying on encapsulation methods for perceived fire safety.
In essence, we are simply aiming to shift design perspectives to efficiently utilize wood's material properties. By not simply being guided by current structural systems and standard tests, but by designing appropriately for wood, new concepts may be explored.
There are still many studies needed in acoustics and connections, to name a few, but these should also be addressed by first understanding the fundamental properties of wood, thus making way for structural innovation.